So welcome to this tutorial video for Bayes, where in this video we're going to look at design for the logistic regression model. And to do that we're going to use the aceglm function, which is in the Bayes package. And we're going to find a pseudo-Bayesian A-optimal design and then a decision theoretic design under the negative squared error loss. And in each case we're going to be doing this for the same logistic regression model. So for more details on this, see section 4.2 of the Bayes vignette, which is on archive. So in Bayes and aceglm, a logistic regression model assumes that each of the responses, which is going to be denoted by yi, is independent and from a Bernoulli distribution with success probability pi I. So yi will be 1 with probability pi I and 0 with probability 1 minus pi I. And this is true for each of our runs 1 up to n. So we have a model for pi I, which is that logit of pi I is equal to the linear predictor e to I, and that's given by this form here. So theta are p unknown parameters, xi is k design variables for the ith run, and then f is a regression function. So it's a standard logistic regression model. So Bayesian design of experiments begins with the specification of a utility function denoted by u, and this is a function of the parameters, the responses for the complete experiment, so vector y, which is y1 up to ym, and then the design, which is the vector of design variables for each run, so x1 up to xn. The utility depends on parameters and responses, both of which we do not know before we do the experiment, so we define the quantity called the expected utility, which is the expectation with respect to the joint distribution on responses and parameters of the utility function. And the Bayesian design is given by maximising this expected utility over the design space. Quick point here, which we'll come back to later, is that we can rewrite this expectation as being an outer expectation with respect to the prior and an inner expectation with respect to the responses. So in this example we're going to consider the negative squared error loss, or NCEL utility, and that's where we look at the minus the sum of the squared differences between the parameters and their posterior mean. So recall that we've got the expected utility for the NCEL utility, and it's got an outer expectation with respect to the prior and an inner expectation. We can actually approximate this inner expectation using the trace of the inverse Fisher information matrix. And the design that maximizes the prior expectation of this approximate utility is called pseudo-Bayesian A-optimal. So here's the setup for the experiment coming from this paper here, the ACE paper. So there's going to be k equals 4 factors. The regression function is such that we're going to have an intercept and then just first order terms for the design variable, so that means there's going to be 5 parameters. Each design variable is such that each element can lie in the interval -1 to 1, and we're going to consider having just 6 runs. And we're going to define designs under pseudo-Bayesian A-optimality and then the full negative squared error loss using the function aceglm. The prior distribution is such that they're going to have independent uniform prior distributions for each element of theta. And first of all, to use aceglm, we first need to specify a seed for reproducibility, the value of n, the value of the number of parameters p, and k, the number of design variables. We generate a starting design given by a random Latin hypercube, and we scale the elements to lie in the interval -1 to 1, and then we need to name the columns of this starting design, and we name them x1 up to x4. So here's the utility function, the expected utility function under pseudo-Bayesian A-optimality, and we need to approximate this integral because it won't be available in closed form, so we're going to use quadrature. So you see the Bayes paper for more details on that. So to use this quadrature method, we need to tell aceglm the prior distribution for theta. So aceglm supports uniform and normal prior distributions when using quadrature. To specify the uniform prior distribution, we let prior be a list containing one element, a matrix named support, where the rows specify the lower and upper limits for each element of theta respectively. So A1, this vector A1 gives the lower limits for each element of theta, and A2 gives the upper limits. So prior is going to be a list, one element called support, which is a matrix with first row given by the lower limits and second row given by the upper limit. So unlike aceglm, we do not need to name the columns of support. So aceglm takes three mandatory arguments. The first is formula, which gives the usual R symbolic description of the model, and that means it actually just specifies the regression function f. In our example, it's going to be x1 plus x2 up to x4. We don't need to specify the intercept, that's specified automatically. So the terms in this formula must match the names of the column headings in the starting design start.d. Next mandatory argument is start.d, and this specifies the n by k initial matrix for the ACE algorithm, and in our example it was the object we'd called start.d. The last mandatory argument specifies the prior distribution for theta, and we do this using the object we created earlier called prior. Optional arguments, we're going to specify a pseudo-Bayesian A-optimality by setting criterion equals to A, and we specify the logistic regression model by using the normal family argument and setting it equal to binomial. We now call aceglm with the mandatory and optional arguments we just discussed. So we're going to call this object x411. Formula is, the argument here is the formula, argument for binomial, argument specifying the starting design, argument specifying the prior, and argument specifying pseudo-Bayesian A-optimality. So aceglm will return a list of class ACE, so x411 will be a list of class ACE. You can use it to access the phase 1 and phase 2 design as follows. So here's the complete phase 2 design, here's the complete phase 1 design. They look identical up to reordering of the row. We now consider the n-cell utility in full, and we do this by changing the optional argument criterion to be n-cell norm. So this will implement a Monte Carlo approximation to the expected utility, where we're using a normal-based approximation to the utility function. So you see the ACE-Bayes vignette for details. Under this method, the argument prior in the aceglm function should now be an R function generating a sample from the prior distribution. And this function below will do that for this example. We now call aceglm with the mandatory and optional arguments as before, so we've changed criterion to be n-cell norm, and now the object prior is changed to be a function, and we've called this object x412. As before, aceglm will return a list of class ACE. We can check the approximate convergence of the ACE algorithm using the S3 method plot. So doing plot of x412 will give us a trace plot of the approximate expected utility with respect to phase 1 iterations. You can see there's large initial increases and then kind of flattening off. And then the grey line gives us the phase 2 iterations, which you can see doesn't seem to approve the design in this case. We can now compare the pseudo-Bayesian A-optimal design, which is x411, to the design found under the normal-based approximation to the Snezzle n-cell utility. We can do that using the assess function. So you can see here's the mean approximate expected n-cell utility for the design found under the normal approximation and under the pseudo-Bayesian A-optimality approximation. You can see the increase in expected utility. A should actually be repeated C times, where C is greater than 1, from different initial designs. This can be achieved using the pace-glm function, and see the video for ACE-NLM for a similar example using the pace-NLM function. So thank you for watching.